Alright, so what we're going to talk about is solving first order differential equations using the exact method. So when we use usually when we're using the exact method, we have to deal with a differential equation that's been written of this form. Right? Sometimes we have the variables y and x, but in this case I decided to use y and t. So usually the differential equation can be written in this form. Some function m of y comma t times dt plus another function n of y comma t times dy. Now obviously this is an implicit differential equation where y is the solution is to involve y implicitly, right? So the solution to this differential equation is not going to look like y of t is equal to something something something. It's not going to look like this. Rather, it's going to look like a function f of y comma t is equal to some function c. Okay, so we see that the y is implicitly involved in the solution. Okay, so we're going to be looking at how to solve this differential equation using the exact method to get an implicit solution like this. Okay, so sometimes the differential equation is also written as m of y comma t plus n of y comma t multiplied by dy dt equals 0. And this is still the same thing, right? There's no big deal about this. It's just that the dt has been divided through, so you have a dy dt here. Okay. So the way we solve this kind of differential equation is first we have to check to make sure if this is an exact equation, if this equation is exact. So what do I mean by exact? Well, we take a look at m and n. Now remember, m and n can be, they're just two different random functions, right? So they symbolize two separate functions. And we take a look at it and we say, well, is dm dy equal to dn dt, right? So we ask ourselves, well, is dm dy equal to dn dt? Now the reason for this, the reason we take a look at this, I'm going to talk a little bit about very soon. But the first step we want to take is to check to make sure if the derivative of m with respect to y is equal to the derivative of n with respect to t. If it is, then the equation is exact. All right, so we can say, if so, put a question mark here. If so, then exact. Okay, so if it is, then the equation is exact. So now that we know that the equation is exact, what do? Well, we propose that because it's exact, that there has to exist some function f, right? So we say there exists an f of y comma t such that df dt is equal to m and df dy is equal to n. Okay, so because this is true, then there exists an f of y comma t such that the partial derivative of f with respect to t is equal to m, and the partial derivative of f with respect to y is equal to n. The reason behind this has to do with the equality between partial derivatives, right? If you have a function f of y comma t, let me write it here, f of y comma t, and we take the derivative, let's take the derivative of f with respect to y first. So let's do df dy. Alright? So we could write this in shorthand as f sub y. Right? So we first take the derivative with respect to y, and then we derive a second time, but this time with respect to t. So Now we say, okay, I want to take the derivative with respect to t of fy, right? So that's going to be equal to the derivative of fy dt, and we can write this as f sub yt. Right? Sometimes it's written the other way around. I'm not entirely sure if it should be f sub ty or f sub yt, so let me not even go there. Let me just write this as d dt of df dy, just so we don't cause any confusion. So we see that here that f of y comma t has first been derived with respect to y, and now is being derived with respect to t. Okay? Now this this approach is the same as if we derived with respect to t first, and then with respect to y. So I would get the same thing if I did df dt, and then I did d dy of f sub t is equal to d dy of df dt. Right? So I'm saying that these two are the same thing. Right? It doesn't matter if I derive with respect to y first and then t, or if I derive with respect to t first and then y. So I can write this as d dt of df dy is equal to d dy of df dt. Okay? So this is the equality between partial derivatives. It doesn't matter which order you take the partial derivative with, as long as you're taking it with respect to the same two variables, the derivatives will be the same. So what does this have to do with part 2 here of solving this differential equation? Well, if you take a look, df dt is equal to m, right? So we can write, let me shift this up a little bit. So we can write this, since df dt is equal to m, I can write m over here for df dt. And df dy is equal to n. I can write n over here for df dy. So that means that dn dt is equal to dm dy, right? So this here is the condition, the first condition that we were checking, right? Our condition was that dm dy must be equal to dn dt. And from what we just said about equality between partial derivatives, right, we see that we get the same thing. Dm dy is equal to dn dt. So this is why that it makes sense that there has to exist a function f of y comma t such that this and this are true, right? If the differential equation is exact, then there exists a function f of y comma t such that this and this are true. Okay? So let's take a look at a problem. Before we do that, once we determine that the differential equation is exact, the third step that we want to do is to solve for f. Obviously, we want to solve for f of y comma t, right? We want to find the function f of y comma t so that we will know what the solution for this differential equation is, right? And our solution would be in the form of f of y comma t is equal to some constant c, right? Our solution would be in this form. F of y comma t is equal to some function c. So we need this. Okay, so in this problem, we're supposed to verify that the given differential equation is exact, and then we're supposed to solve the differential equation. Okay, so if you remember, the first thing we want to do is check to see if the equation is exact. Okay, so this equation is already given to us in the standard form, right? M dt plus N dy is equal to 0, right? So in this case, M is equal to 2t plus 3y, and N is equal to, sorry, I put an X over here. It should be t. So 3t, so 3t plus 2y times dy is equal to 0. So N is equal to 3t plus 2y, and we have to solve, we have to verify to see if this equation is exact. So remember, the way we verify is to take the derivative of m, this function here, with respect to y, and then the derivative of n with respect to t. Okay, so dm dy is going to be equal to d dy of 2t plus 3y, and that's going to give us simply 3. Now, dn dt is equal to d dt of 2t, 3t plus 2y, and that's also going to be equal to 3, right? So these two are equivalent. Now, since they're equivalent, that means that the differential equation is exact, right? So exact. Okay. So since it's exact, we can say that there exists an f of y comma t such that df dt is equal to m, right? This m here is actually the partial with respect to t of this function f. So df dt is equal to 2t plus 3y. And df dy is equal to 3t plus 2y. Okay? So because the equation is exact, this is true. Okay? Now all we have to do now is solve for f. Okay? So we can choose whichever one of these two equations to use to solve for f. We can go with df dy or df dt. Either one is going to give us the same result. So what we're going to go with is df dt. So we're going to start with df dt is equal to 2t plus 3y, which means that the integral of df is equal to the integral of 2t plus 3y times dt. Okay, so this gives us f of y comma t is equal to t squared plus 3yt. Okay, so f of y comma t is equal to t squared plus 3yt. Now when you integrate, you always have a constant of integration, right? So in this case, because we were integrating with respect to t, our constant of integration has to be a function of y. Okay, so our constant of integration is a function of y. So plus g, some function g of y. If we can solve for g of y, then our solution will be complete. So our next step is to solve for g of y. The way we're going to solve for g of y actually is by making use of the fact that the derivative of f with respect to y is equal to n, right? The derivative of f with respect to y is equal to 3t plus 2y. So we're going to use this little fact here to try to solve for g of y. And we do that by taking the derivative of f with respect to y. Alright, so df dy is going to be equal to Now if we take the derivative with respect to y, t vanishes. This 3yt becomes simply 3t. So we have df dy is equal to 3t plus g prime, right? G prime of y. So df dy is equal to 3t plus g prime of y. And we said df dy must be 3t plus 2y. So 3t plus g prime of y is equal to 3t plus 2y. And this means that 3t cancels, and that implies that g prime of y is equal to 2y. Okay. Now we integrate both sides and we find that g prime of y dy integrated is equal to the integral of 2y dy. Okay, so we're integrating both sides here in order to get g of y again. Once we get g of y, we will know what g of y is. That way we can complete the solution. So g of y is equal to y squared plus a constant, right? So g of y is equal to y squared plus k. Now that we know what g of y is, we can go back and say that f of yt is equal to t squared plus 3yt, and now plus our g of y. Our g of y is y squared plus k, so we have y squared plus k. Okay, and this is the solution to the equation. Usually you'll see the solution written as k, the constant, is equal to some function of y comma t. So we can do that. We can, in fact, we can say that f of y comma t is equal to this, which is equal to 0, and then rewrite it so that we can say, if we move the k to the other side, it would be a minus k. So, let's not be too picky. We could just call it c. Right after we move the k over here, we can call it c. And then we would have c is equal to f of y comma t, which means c is equal to t squared plus 3yt plus y squared, which is the same form as this over here. C, the constant, is equal to some function of y comma t. Okay, so this is just a quick step-by-step process to solving for the solution for a differential equation using the exact method. All right, so remember to use the steps that we went over. First, verify to see if the differential equation is exact, and then apply the theorem that if the differential equation is exact, then there has to be a function f such that its partial derivatives are the functions that were given. After that, it's all up to just solving for the function f and then getting your solution and writing it in this form.